Hello friends, welcome back to my YouTube channel. In this class I am going to discuss some unsolved problems of second law of thermodynamics and Carnot's theorem. And these problems are from the p.k.nag's Engineering Thermodynamics book, and those are problems of chapter 6. Every problem will be solved in this chapter, and in this first lecture I am going to solve first 5 problems of chapter 6. Before starting, I must say one thing to all of you. Please do subscribe to this channel, and of course like it and subscribe. Like it and share it to your friends. Let's get started. You see, the question is like this. First question: an inventor claims to have developed an engine that takes in 105 megajoule at a temperature of 400 Kelvin, rejects 42 megajoule at a temperature of 200 Kelvin and delivers 15 kilowatt hour of mechanical work. Would you advise investing money to put this engine in the market? So यहाँ जो engine which operates between two temperature levels TH, जो source temperature है 400 Kelvin higher temperature level, and lower temperature level जो है 200 Kelvin. An engine is operating between these two levels, temperature levels, and it extracts 105 megajoule of heat and rejects 42 megajoule and produces work 15 kilowatt hour. We are going to discuss whether whatever claims the inventor has made is genuine or not. That we are going to study. You know, the efficiency, the maximum efficiency of any heat engine that operates between these two given temperature levels will be the efficiency of a reversible heat engine, because we know that the efficiency of a reversible heat engine is always higher than that of an irreversible heat engine operating between same two temperature levels. And the efficiency of any reversible heat engine is like this: 1 minus TL upon TH. यहाँ हो जाएगा 1 minus 200 Kelvin. TL is the temperature of sink expressed in terms of Kelvin divided by 400. ये हो जाएगा 1 minus 1 by 2, that is 1 by 2. 1 by 2. So we know that this is the maximum possible efficiency insofar as these two temperature levels are concerned. कोई भी हीट इंजन अगर ऑपरेट करेगा इन दोनों के बीच, the efficiency of that heat engine cannot be higher than this 50%, 1 by 2 or 50%. So we know that efficiency is nothing but W by Q. W is the work output, and Q is the heat input. So W by Q, efficiency is nothing but W by Q. So W by Q is equal to 1 by 2. So this actually W max, maximum इतना work ही produce हो सकता है from a given heat input. Q is given to be 105 megajoule. Q ये जो है 105 megajoule है. So in place of Q I will write 105 megajoule मतलब 105,000 kilojoule is equal to 1 by 2. From this what I can conclude is W max, maximum work अगर 105 megajoule से कितना maximum work हो सकता है, W max is equal to 105 divided by 2 kilojoule. ये हो जाएगा किलोजूल. सो इतना ही मैक्सिमम वर्क प्रोड्यूस किसी भी इंजन कर सकता है. एनी हीट इंजन कैन प्रोड्यूस दिस मच अमाउंट ऑफ वर्क एट मैक्सिमम if it operates between two given temperature levels 400 Kelvin and 200 Kelvin, and heat input to the heat engine is 105 megajoule. So इसको अगर हम if you want to convert this into kilowatt hour, we know that 1 kilowatt hour is equal to 3600 kilojoule. So this kilojoule matlab, if you want to convert this into kilowatt hour, this will be kilowatt hour. This comes out as, ये कुछ भी नहीं है, 52,500 divided by 3600, 14.583 kilowatt hour. So at maximum level, any heat engine can produce this much. But as per the question, as per the claims made by the inventor, his engine can produces or delivers 15 kilowatt hour of mechanical work, which means it is not a genuine claim. It is not possible. It is not possible for any heat engine to produce 15 kilowatt hour of work, mechanical work. ये पॉसिबल नहीं है. 15 kilowatt work can never be produced by any heat engine operating between two temperature levels 400 Kelvin and 200 Kelvin and extracting heat of 105 megajoule from source high temperature of 400 Kelvin. No way this is possible. So at maximum this amount of work can be produced, that is 14.5833 kilowatt hour. 15 kilowatt hour of mechanical work can never be produced. So his claims are not true. His claims are not justified. क्योंकि कार्नोट के थ्योरम के अनुसार हीट इंजन, रिवर्सिबिलिटी इंजन का एफिशिएंसी इज हायर देन एनी अदर हीट इंजन, मतलब रिवर्सिबिलिटी इंजन, and efficiency of any reversibility engine is 1 minus sink temperature by source temperature, and both temperatures are to be expressed in Kelvin. From that we determine that maximum work that can be produced by any heat engine is 14.5833 kilowatt hour. On the other hand, the claims of inventor is that his engine will deliver 15 kilowatt hour of mechanical work, which is impossible. So these claims are not genuine. So why, if his claims are not genuine, we cannot afford to invest money in this fictitious engine. So this engine is a fictitious one and we can't afford to invest in this particular engine, to put this engine into market. Second question is like this: if a refrigerator is used for heating purposes in winter so that the atmosphere becomes the cold body and the room to be heated becomes the hot body, how much heat would be available for heating for each kilowatt input to the driving motor? The COP of the refrigerator is 5 and the electromechanical efficiency of the motor is 90%. How does this compare with resistance heating? You see, we know that refrigerator and heat pump are work consuming devices, and refrigerator can be used as a heat pump in winter. The same refrigerator which is used to maintain a temperature lower than the temperature of surrounding. What is the basic function of refrigerator? Refrigerator is a device which maintains the temperature of a space at a level lower than the temperature of surroundings. On the other hand, heat pump is used to maintain the temperature of a house in winter at a level higher than the temperature of surrounding, because in winter the temperature of surrounding is quite low. So if you want to maintain the temperature of a room at a higher level than that of surrounding, then you have to use that heat pump. Same refrigerator can be used as heat pump, only the purpose changes. So you see, we know that refrigerator, suppose this is the low temperature. Here when refrigerator starts functioning as a heat pump, and their this room has to be maintained at a temperature of suppose TH, and this is atmosphere. A room to be heated becomes hot body and atmosphere is the cold body. atmosphere is obviously less than, its temperature is less than this temperature, and refrigerator operates. This is suppose work input. So this is heat to be supplied to the room to maintain its temperature at a level higher than the temperature of the surroundings. So you see, it is given that the COP of refrigerator is given to be 5. COP of refrigerator is 5. We know that COP of heat pump is equal to COP of refrigerator plus 1. That is equal to 5 plus 1, 6. Agar the same device if operates as a refrigerator, its COP would be 5. Then if it operates as a heat pump, its COP will be 6, 5 plus 1. This is the COP of heat pump is equal to COP of refrigerator plus 1. And what is COP of heat pump? COP of heat pump is QH. COP of heat pump is QH divided by W in. QH divided by W in. ये पूछा है फॉर हीटिंग फॉर ईच किलोवाट इनपुट टू द ड्राइविंग मोटर. You know, in the refrigerator or heat pump, we know that same refrigerator which consists of evaporator, compressor, condenser, and expansion valve, and the same can be used as a heat pump. So there is a motor in compressor which extracts electrical energy and convert it into mechanical energy. We know that motor converts electrical energy into mechanical energy. Here it is given that the electromechanical efficiency of the motor is 90%. मतलब अगर 1 किलोवाट एनर्जी ये एक्सट्रैक्ट करेगा, इलेक्ट्रिकल एनर्जी लेगा, the amount of energy mechanical work that it will produce is 0.9, क्योंकि ये 1 किलो जूल को 0.9 किलो जूल में कन्वर्ट करेगा, क्योंकि इट्स एफिशिएंसी इज 90%, electromechanical efficiency of 90%. So in the question it is asked to find out whatever heat would be available for heating the room, what amount of heat would be available for heating the room, so that the temperature of inside the room will be maintained at a higher temperature than that of surrounding per kilowatt of इलेक्ट्रिकल एनर्जी, पर किलोवाट ऑफ इलेक्ट्रिकल एनर्जी. ये जो कंप्रेसर में जो मोटर है, ये जो वर्क इनपुट ऑलवेज रेफर्स टू मैकेनिकल वर्क इनपुट, क्योंकि कंप्रेसर में जो पार्ट्स है ये सब मूव करता है. जो मोटर जो इलेक्ट्रिकल एनर्जी लेता है, उसका द मेन फंक्शन इज टू मूव ऑल द पार्ट्स. दैट मीन्स मैकेनिकल वर्क इज रिक्वायर्ड. सो W in here refers to mechanical work. But in the question it is asked for each kilowatt input to the driving. Input क्या है? ड्राइविंग मोटर को input electrical in the form of electrical energy. So that means if you supply 1 kilowatt of electrical energy to motor, what is the amount? Motor is inside the compressor, but this W in the diagram, this COP, you know, QH divided by W in, ये जो W in रहता है, that refers to mechanical energy only, not electrical energy. So COP of heat pump, QH divided by W in. QH is the heat available for heating the room here, and W in here refers to mechanical work, mechanical energy input. And in the question it is asked, अगर हम 1 किलोवाट इलेक्ट्रिकल एनर्जी देंगे मोटर को तो कितना हीट अवेलेबल होगा, ये क्वेश्चन है. सो अगर 1 किलोवाट एनर्जी हम देंगे, यहाँ से जो होता है COP ऑफ हीट पंप इज 6 इज इक्वल टू QH डिवाइडेड बाई W in. सो यहाँ W in कितना आएगा? W in इज मैकेनिकल वर्क इनपुट. W in इज मैकेनिकल वर्क इनपुट फॉर 1 kilowatt electrical input, energy input to motor. Motor is inside the compressor, motor of compressor. Mechanical work produced is 0.9 kilowatt. Since the electromechanical efficiency of motor is 90%, so ये 1 kilowatt को 0.9 kilowatt में convert कर रहा है. So in place of W in, I will write 0.9 kilowatt, not 1 kilowatt, क्योंकि हम तो 1 किलोवाट इलेक्ट्रिकल एनर्जी दे रहे हैं मोटर को, लेकिन मैकेनिकल वर्क जो इनपुट हो रहा है वो इलेक्ट्रिकल एनर्जी 1 किलोवाट इज सेम एज मैकेनिकल एनर्जी 0.9 किलोवाट, क्योंकि इलेक्ट्रोमैकेनिकल कन्वर्जन और एफिशिएंसी ऑफ मोटर इज 90%. सो 6 इज इक्वल टू QH divided by, ये W in refers to mechanical work input, not electrical work input. W in is 0.9. Hence, QH is equal to 6 multiplied by 0.9, that is 5.4 kilowatt. So, if you supply 1 kilowatt electrical energy to motor, the heat available for heating the room or available for maintaining the temperature of a room at a higher level than the temperature of surrounding will be 5.4 kilowatt. On the other hand, if we will use direct heating, resistance heating for the room, if we supply 1 kilowatt electrical energy to a heater, the heat energy produced will be same 1 kilowatt only. So if you use heat pump instead of the resistance heating, there will be a huge advantage, thermodynamic advantage, because ये केस में अगर हम 1 किलोवाट इलेक्ट्रिकल एनर्जी दे रहे हैं, द हीट प्रोड्यूस्ड इज 5.4 किलोवाट. हीट अवेलेबल फॉर हीटिंग द रूम इज 5.4 kilowatt. In case of resistance heating, if you supply 1 kilowatt electrical energy, you will be able to produce a heat of that equal amount only, that 1 kilowatt only. But here, by supplying 1 kilowatt electrical energy, if you use the heat pump or refrigerator, then you are finding out 5.4 kilowatt. So you will be having a huge advantage. So answer is 5.4 kilowatt. So 5.4 kilowatt amount of heat will be available for each kilowatt input to the driving motor. The third question is like this. Using an engine of 30% thermal efficiency to drive a refrigerator having a COP of 5, what is the heat input to the engine for each megajoule removed from the cold body by the refrigerator? If the system is used as a heat pump, how many megajoule heat would be available for heating for each megajoule of heat input to the engine? So question is like this. An engine operates a refrigerator here. We know that an engine produces some work. Suppose this is source temperature for engine and heat engine operates. This is heat input, heat engine. This is refrigerator. So you see, using an engine of 30%, suppose this is Q1, Q2, Q3, this is Q4. Heat engine, in this case, a heat engine drives a refrigerator. That means whatever work is produced by this heat engine goes on to drive the refrigerator. And COP of refrigerator is 5. COP of refrigerator is 5. COP of refrigerator is Q3 by W. Q3 by W is 5. Then what is the heat input into the engine for each megajoule removed from the cold body by the refrigerator? So Q3 suppose is 1 megajoule. Here the Q3 is the amount of heat that is removed by the refrigerator from the cold body. Here is T3. So if Q3 is 1 megajoule, then what is the heat input to the engine? First bit में ये पूछा है. Q1 is how much? Q1 is how much? You see, here whatever work is produced by heat engine is the work input for refrigerator. Efficiency of heat engine, we know that 30% it is given, and this is nothing but work output divided by heat input, W by Q1. W is the work output for this heat engine and Q1 is the heat input. W by Q1 is 0.3. W by Q1 is 0.3, 30% or 0.3. And COP of this particular refrigerator is given to be 5. Q3 by W is equal to 5. From this, we can find out the ratio of Q3 by Q1. If you multiply this with this, what I will get? Q3 by W multiplied by W by Q1 will be, in place of Q3 by W, I will write 5 into W by Q1 is 0.3. Why it is 0.3? Because it is given that the efficiency of the engine is 30%. Efficiency of heat engine is W by Q1. 5 into 0.3, that is 1.5. यहाँ से क्या आ रहा है? Q3 by Q1 is equal to 1.5. So it is asked to find out what is the heat input to the engine. The heat input into the engine for each megajoule removed from the cold body by refrigerator. So this will be, you see, we are required to find out Q1 by Q3. हीट इनपुट कितना आएगा इंजन को पर ईच मेगाजूल रिमूव्ड फ्रॉम द कोल्ड बॉडी. दिस इज द हीट एनर्जी रिमूव्ड फ्रॉम द कोल्ड बॉडी, दैट इज Q3. अगर Q3 1 मेगाजूल है तो व्हाट इज द अमाउंट ऑफ Q1? दिस हैज बीन आस्क्ड. सो वी आर रिक्वायर्ड टू फाइंड आउट Q1 by Q3. If Q3 by Q1 is 1.5, then Q1 by Q3 will be 1 by 1.5 megajoule. 1 by 1.5 megajoule. So if you want to express this in terms of kilojoule, that will be 1 by 1.5 multiplied by 1000 kilojoule. So this will be 1000 by 1.5 kilojoule. That answer will be 666.667 kilojoule. So this is the amount of heat input to the heat engine. यहाँ Q1 का वैल्यू इतना होगा अगर Q3 1 मेगाजूल होगा. And second bit is, so first answer to first bit is 666.667 kilojoule. In terms of megajoule, it will be 1 upon 1.5. So if the same system is used as a heat pump, we know that refrigerator can also be used as a heat pump. How many megajoule of heat would be available for heating? How many megajoule of heat would be available for heating? So what will be the value of Q4? That has been asked. This is the heat energy available for heating. This is the heat removal. This Q3 is the rate of heat removal and Q4 is the amount of heat available for heating. So it has been asked to, if the system is used as a heat pump, मतलब ये heat supply करेगा. How many megajoule of heat would be available for heating for each megajoule of heat input to the engine? मतलब Q4 divided by Q1 we have to find out. Q4 divided by Q1. Q4 divided by Q1. अगर ये है Q3 by W is equal to 5. Q3 by W is equal to 5. COP of refrigerator is given to be 5. Q3 divided by W, that is 5. So COP of heat pump is nothing but the COP of heat pump is equal to COP of refrigerator plus 1. So it is equal to 5 plus 1 6. रेफ्रिजरेटर का COP 5 दिया हुआ है. So COP of heat pump is nothing but Q4 by W. Here in this case, if this same refrigerator is used as a heat pump, its COP will be Q4 by W. And if it is used as a refrigerator, the COP will be Q3 by W. So Q4 by W. Q4 by W is equal to 6. So what is required to find out is Q4 by Q1. Matlab, we know that Q4 by W is 6 and W by Q1 is already given to be 0.3, 30%. So if you multiply this Q4 by W into W by Q1 is equal to 6 multiplied by 0.3, it is 1.8. 1.8. So it will be just a ratio. So 1.8 megajoule, 1.8 megajoule. Multiplication of these two ratios. So if Q4, so the question, second bit, the question is फॉर ईच मेगाजूल ऑफ हीट इनपुट कितना हीट अवेलेबल होगा. तो Q4 कितना होगा. अगर Q1 1 मेगाजूल है, Q1 1 मेगाजूल है, अगर हम हीट इंजन को 1 मेगाजूल सप्लाई करेंगे, यहाँ कितना अवेलेबल होगा. Q4 डिवाइडेड बाई Q1, दैट इज 1.8. Q4 डिवाइडेड बाई Q1 आ गया 1.8. Q4 by Q1 is 1.8. So if Q1 is 1, it is asked, if Q1 is 1 megajoule, then what will be the Q4? Q4 is equal to Q1 1 megajoule into 1.8, matlab 1.8 megajoule. So if you supply 1 megajoule of heat input to the heat engine, the heat available for heating, if the refrigerator is used as a heat pump, would be 1.8 megajoule. 1.8 megajoule. So fourth question is like this. An electric storage battery which can exchange heat only with a constant temperature atmosphere goes through a complete cycle of two processes. In process 1 to 2.8 kilowatt hour of electrical work flow into the battery, while 732 kilojoule of heat flow out to the atmosphere. During the process 1 to 2 energy interactions takes place. Electrical work is given into the battery and this amount of heat is removed. During the process 2.1, 2.4 kilowatt hour of work flow out of the battery. लेकिन जो process 2.1 में इतना work flow out हो रहा है. So find the heat transfer in the process 2.1. So from first law of thermodynamics, Q is equal to delta E plus W. This relation we know. Q is equal to delta E plus W, or simply we can apply any energy balance equation. Q is equal to, if Q is the heat supplied to a system and W is the work output from the system during a particular process, and delta E is the change in energy or internal energy. So for process 1-2, if you use this equation for process 1-2, for process 1-2, Q12 heat, in this equation Q is the heat input into the system, but in this case in process 1-2, 732 kilojoule of heat flow out to the atmosphere. So ये system से बाहर हो रहा है. So in place of Q I'll write -732 is equal to E2 minus E1 delta E plus W12 in this equation is work output, but here the work is input, work is supplied in form of electrical work, and that amount of work is 2.8, that will be minus sign has to put 2.8 multiplied by 3600 kilojoule. 1 kilowatt hour is 3600 kilojoule, and this is kilojoule. And if you calculate E2 minus E1 energy at state 2 minus energy at state 1 is equal to 9348 kilojoule. Then for process 2-1, for process 2-1, for process 2-1, Q21 is equal to delta E मतलब energy at final state. Here the final state is E1 minus E2 plus W12. So यहाँ W12 जो है W21 not 12 W21. So if E2 minus E1 is equal to 9348 kilojoule, E1 minus E2 will be minus of that, minus 9348 kilojoule plus, you see it is given that during the process 2-1 this amount of work flow out of the battery, 2.4 kilowatt hour of battery. So it will be plus sign will be put before this 2.4. If you want to convert this into kilojoule, 3600 has to be multiplied. So this becomes is equal to minus 708 kilojoule. So it has been asked to find the heat transfer in the process 2-1. So our answer will be, there will be a removal of heat to the amount of 708 kilojoule. मतलब 708 kilojoule of heat will flow out towards atmosphere. So since it is a negative sign, and when heat is removed from a system, it is negative. So during the process 2-1, heat transfer will be minus 7. Find the heat transfer in the process 2-1. So it will be minus 708 kilojoule, or heat will flow from the atmosphere, to the atmosphere. So second bit, you see, if the process 1-2 has occurred as above, does the first law or second law limit the maximum possible work of process 2-1? Then you see, we know that low grade energy cannot be completely converted into high grade energy, but high grade energy can be completely converted into low grade energy. So since in this case electrical energy is supplied to battery, the whole amount of electrical energy can be converted into work, that is high grade energy. So there is no problem. So second law says that whatever energy is given into the battery in form of electrical energy, that is a high grade energy, that can be converted to work. So that puts a limitation on, in this case, agar supposing that the process 1-2 occurs as it has occurred in this case, then ये पूछा गया है, then you have to find out what is the maximum possible work. क्योंकि इलेक्ट्रिकल एनर्जी तो कन्वर्ट हो सकता है, देर इज नो लिमिटेशन imposed by second law. Second law only says that low grade energy cannot be completely converted into high grade energy, but one form of high grade energy can be converted into other form of high grade energy. So that's why what will be the question answer would be only second law puts a limitation. So what is the maximum possible amount of work that can be produced according to second law? We know that E in माइनस ई आउट ईयर निकालेंगे. ई इन मतलब अगर बैटरी को एक सिस्टम ले लेंगे तो इसमें कितना एनर्जी इन हो रहा है और कितना एनर्जी बाहर जा रहा है. ई इन इज 10,080 बिकॉज यहाँ 2.8 kilowatt during the first process, this amount of work is flowing into the battery, energy in 2.8 kilowatt hour. उसको अगर हम जूल में कन्वर्ट करेंगे, ये आएगा 10,080 किलो जूल माइनस, और एनर्जी प्रोसेस 1-2 में कितना बाहर जा रहा है एनर्जी, 732 किलो जूल तो बाहर जा रहा है ना. ये लिखा गया है द प्रोसेस 1-2 हैज ऑकर्ड आज है, वो मतलब इतना एनर्जी अंदर आएगा और 732 किलो जूल हीट बाहर जाएगा. उसके बाद जो होगा सो मतलब ई इन माइनस ई आउट ऐसे रहेगा. ये हो गया हमारा 9348 kilojoule. ये जो energy, this is the net energy that enters into the battery, net energy, because this is the energy that enters and this is the energy leaves. So this net amount of energy enters into the battery in form of, this is the net energy entering into battery. So this can be converted into work. This can be converted into work because electrical energy is a high grade energy. Except heat, all other energy is high grade energy. So this can be completely converted into work. So W21 will be 9348 kilojoule. 9348 kilojoule. So maximum possible work that can be produced in process 2-1, and that limitation is imposed by second law only, because second law segregates between various categories of energy, that is high grade and low grade, and it says that only high grade energy can be converted into another form of high grade energy, and high grade energy cannot be converted into, low grade energy cannot be completely converted into high grade energy. But in this case, net energy that enters into battery is in the form of high grade energy, so it can be converted into work, that is 9348 kilojoule. So what will be the heat interaction for the process 2-1? So Q21 is equal to, Q is equal to delta E plus W. So delta E will be here for process 2-1, final state will be 1, initial state will be 2. E1 minus E2 plus WT1. If E2 minus E1 is 9348, E2 minus E1 is 9348. E2 minus E1 is 9348. So E1 minus E2 will be minus 9348 plus W21 is 9348. So this will be 0. There cannot be any heat interaction during the process. So heat transfer in the process 2-1 will be 0. Heat transfer will be 0. So you see, this is the last question. A household refrigerator is maintained at a temperature of 2 degrees Celsius. Every time the door is opened, warm material is placed inside, introducing an average of 420 kilojoule, but making only a small change in the temperature of refrigerator. The door is opened 20 times a day and the refrigerator operates at 15% of the ideal COP. The cost of work is rupees 2.5 per kilowatt hour. What is the monthly bill for this refrigerator? The atmosphere is at 30 degrees Celsius. You see, the household refrigerator operates between these temperatures. The refrigerated space is 2 degrees Celsius or 275 Kelvin, and atmosphere here is, this is the higher temperature body. एटमॉस्फेयर इज एट 30 डिग्री सेल्सियस. उसको अगर हम कन्वर्ट करेंगे केल्विन में, वो आ जाएगा 303 केल्विन. 303 केल्विन. सो रेफ्रिजरेटर इज ऑपरेटिंग. Suppose this is Q2, this is Q1, and this is the work input. So COP is given to be 15% of the ideal COP. So we know that ideal COP मतलब COP of the reversible refrigerator operating between two given temperature levels. That is the ideal COP. If a refrigerator worked on reversed Carnot cycle, then what would be its COP? That is ideal COP. So ideal COP of refrigerator is TL by TH minus TL. TL is this much, this is higher temperature. मतलब 275 Kelvin divided by 303 minus 275 Kelvin. So that is equal to 9.821. 1.43. This is the ideal COP, but the actual COP is 15%, 0.15 of this. This is equal to 1.473. So refrigerator is a body which maintains the temperature of this space at a level higher than the temperature of the surrounding, sorry, lower than the temperature. अगर ये हम डोर को, if you open the door, then the heat will enter because the surrounding is at a high temperature. Some heat will flow into this space. Some heat leakage of heat will take place because heat always flows from high temperature to low temperature. So refrigerator का function है to extract whatever heat enters into this space, it must remove it continuously so that the temperature of this space will be maintained at a level, at an equal level. It will be maintained at 2 degrees Celsius. Only if this amount of heat that enters when the door is opened is removed, then only this space, the temperature of this space will be maintained at a temperature, at a level of 2 degrees Celsius. जो heat आएगा ये इसको remove कर देगा. So what is the heat enters into the refrigerator in a day? And the refrigerator is opened 20 times a day, and every time the door is opened, 420 to 20 kilojoule of heat enters into the refrigerated space, actually refrigerated space. So what is the amount of heat that is extracted by refrigerator, or you can say the amount of heat that is introduced into the refrigerator by opening the door? Q2 is equal to, for every time you open the door, this amount of heat enters, and in a day 20 times the door is opened. So in a day this amount of heat is extracted by the refrigerator in a day, 8400 kilojoule. So we will calculate for a day, then eventually we will calculate for month. So in a day, this is the amount of heat extracted by the refrigerator. So we know that COP is equal to Q2, COP of this particular refrigerator will be Q2 by W, Q2 by W. So मतलब 8400 by W, this is the energy input, energy required or work required, is equal to this will be having no unit because COP this is 1.4732. So यहाँ से हम W निकाल सकते हैं. So work required per day, 8400 divided by 1.4732, 87 kilojoule. That will be, if you divide this by 3600, it will be converted into kilowatt hour. 1.5838 kilowatt hour daily इतना energy required होगा. So cost of work is given in the question. Cost of work is rupees 2 rupees 50 paise per kilowatt hour. So daily bill will be 1.5838 multiplied by 2.5, इतना rupees. अगर लेकिन it has been asked to find out the monthly bill, not daily bill. So monthly bill, that will be 30 multiplied by 38 to 2.50, इतना रुपीज आएगा, rupees 118.78. This is the final answer. This is the monthly bill for electricity that the refrigerator consumes. That's all. Thanks for watching.